This is the ASME Dynamic System Control Division podcast. I'm the host, Hao, Associate Professor at North Carolina State University. In today's episode, we are very honored to have Professor Aaron Johnson from Carnegie Mellon University as our guest. Welcome, Aaron. Could you please give some introduction about yourself?
Thanks for having me. As you said, my name's Aaron Johnson. I'm assistant professor at Carnegie Mellon in the mechanical engineering department and also in the Robotics Institute. And I'm interested in getting robots out of the lab, out of the factory, and into challenging environments and sort of all of the difficulties that come with that.
Yeah, that's very interesting. Let me start this interview by first congratulations on your recent NSF Career Award. Can you share with us what this project is about and how you are developing this idea from the very beginning?
Yeah, thank you. This project's really focused on understanding contact and how it changes the structure of system dynamics, and really how can we take advantage of that structure to better control systems like legged robots interacting with the world. And the challenge with contact is that it's inherently discontinuous, right? If I have my leg on the ground, it can exert a large contact force. We want to push hard on the ground. But if the leg's just above the ground, a millimeter away, I get zero contact force. And this kind of discontinuity breaks a lot of the standard tools that we have for control, for state estimation, for learning. All of these sort of things generally assume smooth systems.
Yeah.
So in this project, we are looking at how these discontinuities affect the stability of the system, and what can we change about the structure to improve that stability. So for example, we just put out the first preprint from this project on Archive describing what we call hybrid event shaping, where we're able to change the properties of those discontinuous events in order to improve the stability of the behavior. And you should think of this as sort of changing the shape of the approach angle and velocity and acceleration around those hybrid events. And this approach explains and unifies some of the previously known examples of stabilizing controllers, such as swing leg retraction when you're walking, or paddle juggling. To stabilize paddle juggling, you need to have a deceleration in the paddle. As well as providing an approach to produce new controllers on different systems that could take advantage of some of these similar structural properties around these discontinuities.
Okay, I see. I went through your paper very briefly. I think to make robots work in real world, physical interaction is certainly crucial, but also very challenging. I think your work on the collision modeling and will bring some new solutions to this field. And talking about the physical interaction, I think your research is focused on the legged robots, which is very, very popular nowadays. What is the current status of this field? How do you envision the future of this area?
I mean, I think this is a very exciting time in legged robots. When I started my PhD, the only commercially available legged robots were very expensive, large, research-grade humanoid robots that didn't work very well. And so for my PhD work, which was on modeling and control of legged robots, doing jumps and other sort of agile behaviors, we had to build our own small legged robots because there weren't really any other options. And then fast forward today, and there's like a half dozen companies that will sell you a small electric quadruped for as little as a few $1,000s. And so it's clear to me that there's now a real market, right? There's a legged robot market that didn't exist before. It's not just academia, it's not just sort of research labs that are buying these robots. And it's because these robots have now shown that they're capable of being useful for a wide range of applications. Right, and so the customers outside of researchers that are interested in these platforms include things like construction, industrial inspection, and sort of perimeter monitoring type applications. All of these are cases where we need sort of better mobility than you can get with a tracked platform.
I see.
It's been an interesting convergence of design in that quadruped market over time, where the options from Boston Dynamics, Ghost Robotics, Mini Cheetah, Antibiotics, Unitree, all of these have sort of settled on this very similar 3 degrees of freedom per leg kinematics that provides really good dexterity with a relatively simple mechanism. Earlier legged robots had higher numbers of degrees of freedom in each leg, which adds to the cost and complexity. But by having the sort of 3 active degrees of freedom plus 3 passive rotation degrees of freedom at the toe, all these robots have point feet. Gives you very good dexterity, so you can sort of position the body or into any orientation as you're walking.
Yeah,
yeah, go ahead.
Yeah, I think that's really amazing to see like robots are walking out of research labs are becoming part of our daily life, right? I feel that academia and the industry are taking those robots to the next level almost every month, I feel like, yeah. I think your research covers very broad areas, not only like robot. I think you also work on manipulation. What problem are you tackling right now? How to create impactful research in this area? Yeah.
Yeah, as with our legged locomotion work, a lot of the manipulation questions we are asking are centered around questions around contact and uncertainty. And I sort of think of this as, if we want to manipulate our arm or a legged robot to be moving around in interesting spaces, it's going to bump into things, right? That's unavoidable. So we need to design the mechanism, we need to design the controllers to make it okay for our robots to have these kind of unintended contact with the world. And so, for example, we recently built this direct drive hand, the DD hand, that's very transparent to the world, meaning that we can impact the fingers into the ground at high speed. So we can kind of slam the whole hand against the ground. And first of all, survive, right? And not break. I mean, lots of robots try so hard to avoid contact with the world because they're going to either break their fingers or break the world that they're bumping into. But we can not only survive it, but then quickly detect that contact with those sort of proprioceptive capabilities, localize it, figure out where we're touching, and react quickly to move the fingers out of the way or move the arm out of the way. And then all of the tools and approaches we are developing in this manipulation work can easily be transitioned over to legged locomotion and vice versa, which is why I think it's important to think about sort of both classes of problems in my lab. And that's something that I started in my PhD, working out sort of how exactly the kinematics and dynamics map back and forth in what I called then sort of legged self-manipulation, which was really taking all of the analysis tools from the manipulation literature and translating it into the locomotion side.
Yeah, wow. I think that's really cool. It's really inspiring to treat locomotion and the manipulation from somewhat unified framework. I recently heard some new term called physical AI. I think it's kind of like interesting to describe some kind of like the work that you do. And also in my lab, we also do some like a wearable robot physical interaction. I mean, wearing those robots. I think those physical AI really kind of like a new field, both manipulation and the locomotion. I think is maybe the next big thing in the general area. Yeah.
And I think, I mean, it's, everything is more popular if we call it AI now, but this is something that historically would have been called maybe morphological intelligence, right? Anytime you can replace what would otherwise be something computational with something that's coming automatically from the design. Yeah,
I think sometimes it's also called embodied intelligence, right? Some intrinsic intelligence from the machinery itself. I think that's really crucial, and I think it has their own challenges. And I think we are growing this community, this research area. Yeah. I think maybe I have another question is I see that you are also involved with the Black in Robotics organization. Can you tell us more about this?
Absolutely. Yeah. I mean, it should come as no surprise to anyone here that when I say that the demographics of the robotics community or the engineering community are very different from the rest of the country or the rest of the world. And in particular, the number of Black researchers in engineering is very low and has stayed about the same over the last decade. So it's clear that this situation isn't going to change without concerted effort by all of us in the community. So that's why I've joined the Black in Robotics organization. I'm on the Allies committee. Also worked on the Black in Robotics reading list, as well as doing things like organizing the Inclusion at RSS program, and organizing sort of after-school programs for the local nonprofit, and really sort of supporting diverse scholars in robotics and engineering more generally is something that we all need to get involved with and spend real time on.
Yeah, I think this effort is really, really important. It's not only about the research itself, I think, but how to develop a diverse community and also diverse talents. Do you have some suggestions about how the DSCD community can potentially facilitate this kind of effort?
Yeah, well, I think everyone in the community needs to think about what actions they can take individually or as a research group or a school, sort of at every level. And this can start by really just learning more. If you're not sure of what to do first, I encourage you to read this Supporting Black Scholars in Robotics article, as well as there's these really good action item lists at Black in Engineering and Black in Computing sites. And then advocate for change at your school and more broadly. You can join a networking or advocacy organization. So Black in Robotics is one of them. There's also Women in Robotics and other similar sort of networking and advocacy organizations. And finally, I think the biggest one is maybe just spend time to read, cite, mentor, collaborate, and work with a diverse set of researchers. And so things like the Black in Robotics reading list can help with that, as well as the similar ones for women in robotics.